Hello, welcome to Team 3's interim presentation. Today I'm here with myself, Sumin, Navid, George, Sam, Eric, and Will. Our topic is optimized design for manufacturability of a COVID-19 ventilator.
Ventilators were in high demand during the pandemic to help people breathe. The design uses a 3D printed frame and a motor to achieve this function.
Here's a quick view on the assembly CAD that shows the base view of the product. Now, the exploited CAD shows the details of the product. There are total 27 unique parts that go in this design. Please use the table on the left as reference for the names of parts. Here's the motor assembly breakout view as it shows combined in the exploded CAD. It sits right underneath the bottle bottom support, and there will be a switch on the display panel that's connected to the motor. Our primary customers for this product would be hospitals or medical facilities that use ventilators to supply sufficient oxygen to patients with restricted breathing. Secondary customers for this product include ambulances for when a ventilator is needed in the field.
The fast diagram for the ventilator is shown here with the task function of assist respiratory system, the primary functions of adjust pressure and enclose air, and the supporting functions of regulate oxygen, secure interior, enhance portability, show information, enable control, and inhibit vibration.
Next, the team created two assembly sequences for the ventilator assembly. For the first sequence, we tried to combine parts that interacted and made separate sub-assemblies. Moving from left to right, the first subassembly is the rear base. The rear base is then connected to the front base. Once those are assembled, the motor assembly can be added, followed by the squeeze mechanism subassembly. Finally, the control assembly is added last. For sequence 2, we took some more care to how the subassemblies interacted in the first sequence and moved parts to various subassemblies. Again, moving from left to right, we combined the two base subassemblies into one sequence. We then found adding the motor subassembly was better for ease of assembly. Next, the lower squeeze assembly was connected. Finally, the upper squeeze subassembly followed by the control subassembly completed this sequence. The noticeable difference between the two sequences is the ease of fastening and the ease of testing subassemblies. The combining of the bases and moving the lower squeeze subassembly after the motor subassembly allowed for an easier overall assembly process.
Next, we have the function component mapping matrix, where each component of the ventilator is assigned to a leaf function on the fast diagram. You'll notice that most components have one single function, with the most popular being adjust pressure, secure interior, and inhibit vibration. The presence of multiple components on these functions indicates the opportunity to apply design for manufacturing principles on a redesign of the ventilator.
The breakdown of the BOM is shown below. Across the various components, the current design of the housing of the ventilator either requires injection molding, machining, or die casting. Other components such as the electronics, motor, and bottle are purchased off the shelf. Material costs for the machined and molded parts were selected through custompart.net, while the cost of the purchased parts are from the various vendors selected, both assuming an annual production volume of 200,000 units. This iteration of the BOM assumes a full manual assembly, thus the assembly time was chosen through two-digit classifications of each component, and the assembly cost was then calculated assuming a live wage of $19.90 per the national average. The full cost of the ventilator comes out to be $311.69. Next, by classifying the components' functional importance versus cost, we see that the electronics, motor mount pivot, and rods, and ventilator bottle require redesign. The electronics, motor, and bottle cannot be redesigned as they're purchased subassemblies, but cheaper alternatives will continue to be explored. We will also look at more components in the low cost of assembly column, as through the redesign of many of these components, we believe a significant part and cost reduction can be achieved.
From a high level, these products are quite similar. The functional differentiation that is different for each customer group is to enhance portability. The only different component between the two products is the addition of the handle to enhance portability. We can see here the difference between the non-mobile and the mobile unit. Highlighted in red is the handle. The interfaces remain generally the same. You can see those bolt holes that the handle goes into are retained between designs. The primary difference here is the addition of the handle to allow for easier transport and using the unit on the go.
Next, we show the original and optimized assembly sequences. Assembly sequence 2 is optimized with bottle hat and control assemblies completed earlier, allowing motor assembly and display assemblies to finalize the original product. It's important to note that due to the handle design, we are maximizing delay differentiation and applying the handle for the mobile product at the end for both assembly sequences.